Every railroad engineer once agreed, without spokes, a locomotive wheel would buckle under its own power. Then came the disc wheel, solid steel and without spokes, violating every rule and yet promising to revolutionize an entire industry. Tested against decades of failures and doubters, it not only survived, it set off a maintenance and design revolution. Why did the impossible succeed? And how did a forgotten experiment change the fate of American railroading? Let us expose the turning point that defied engineering logic. For more than a century, the spoked wheel stood as the foundation of locomotive engineering. Every major railroad, from the Pennsylvania Railroad to the Union Pacific, relied on this design. Spokes weren't just a stylistic choice, they were a mechanical necessity. Each spoke acted as a bridge, carrying the tremendous weight of the locomotive and its load from the center hub out to the rim. This layout let the wheel flex ever so slightly under the pounding force of pistons and rails, absorbing shocks that would otherwise shatter rigid metal. But the benefits went deeper than just strength. Spokes created a network of pathways for stress, allowing the wheel to distribute the force of every jolt, every track imperfection, across multiple points instead of focusing it in one spot. This was vital for the main drivers, where the side rods and connecting rods delivered their full power. Without this careful spread of stress, cracks would form, often starting at the joints where the spokes met the rim, or at the base near the hub. For decades, engineers saw these failures again and again, but the alternative seemed unthinkable. Heat posed another challenge. As steel wheels braked and rolled, they expanded and contracted. Spoked construction allowed for what engineers called thermal breathing, letting wheels flex as temperatures soared on long runs or during sudden stops. Without this, engineers feared, a wheel could warp or even break apart. All these factors made the spoked wheel seem irreplaceable. It was a design born from experience, refined by disaster, and trusted by every railroad workshop across the country. The stakes were clear. Any attempt to change this formula risked catastrophic failure, not just of a wheel, but of the entire train behind it. To question the spoke was to question the very foundation of locomotive safety and reliability. William Scullan grew up surrounded by the clang and roar of steel mills in St. Louis, Missouri. By the time he joined Scullan Steel Company, the railroad world was locked in a cycle of endless breakdown and repair. Every week, maintenance logs filled with the same complaints: cracked spokes, failed joints, and costly downtime. Workshops scrambled to patch up wheels that had barely finished their last run. For railroad mechanics, it was a losing battle against fatigue and metal stress. The failures always seemed to start in the same places, where spokes met the rim, or around the main pin boss, the heart of the wheel that took the brunt of every piston stroke. Some wheels lasted only a few years before the first hairline fractures appeared. Others made it a little longer, but the pattern never changed. Each repair meant pulling a locomotive from service, costing railroads thousands in lost revenue and emergency fixes. Scullan watched this cycle and refused to accept it as the price of progress. He was not content to keep patching the same wounds. He asked a question no one else dared to ask. What if the problem was not with the steel or the skill of the workers, but with the very idea of the spoke itself? He imagined a wheel with no spokes at all. A single solid disc of steel cast in one piece. No joints to crack, no weak spots for stress to gather. It was a concept so simple and so radical that most engineers dismissed it outright. The accepted wisdom said a wheel without spokes would be too heavy, too rigid, doomed to fail under the heat and pounding of the rails. But Scullan saw only the endless repair bills and the wasted hours in the shops. He believed a new approach was possible, one that would end the cycle of failure and change the way railroads thought about their most basic machinery. The proposal for a one-piece disc wheel was not just a technical suggestion, it was a challenge to decades of tradition and an invitation to imagine something better. A solid disc of steel does not just look different from a spoked wheel, it behaves differently at every turn of the rail. Where a traditional wheel sent force racing along narrow spokes, the disc wheel spread that load across its entire face. Imagine a single, unbroken ring of metal, each push from the piston or jolt from the track absorbed and shared by the whole structure. The weakest points of the old design, the joints at the base of each spoke, and the thin steel around the main pin boss, simply did not exist anymore. Instead, the disc acted as a continuous shell with no sharp transitions for cracks to start. Stress that once concentrated in a handful of places now flowed smoothly from the hub to the rim, following gentle curves instead of bottlenecking at the ends of spokes. The internal shape of the disc was not always solid either. Many featured hollow box sections or carefully shaped ribs cast within the wheel. These acted like hidden bridges, reinforcing the structure while keeping weight down. The result was a wheel that could be lighter than a spoked equivalent, yet stronger where it counted. Hollow chambers inside the disc also left room for precise counterbalancing. Weights could be distributed exactly where needed, reducing vibration and letting locomotives run faster and smoother. This was especially important for main drivers, where perfect balance meant less pounding on the track and less wear on the bearings. Vibration, once a constant enemy, met its match in the disc wheel. The solid face damped out high-frequency shudders from rough track, acting almost like a shock absorber. Instead of flexing and rebounding like a web of spokes, the disc's mass and stiffness soaked up energy and kept the locomotive stable at speed. Engineers found that with the right combination of thickness and internal bracing, the disc wheel could handle sudden impacts and long, punishing runs without developing the hairline fractures that doomed so many spoked wheels. Thermal expansion, the swelling and shrinking of steel as it heated and cooled, posed a challenge. But the disc's continuous rim, free from the stress risers found at spoke junctions, allowed for more uniform growth. Carefully designed vent holes or slots sometimes helped release heat, but the main advantage was structural. Because by eliminating the spoke, the disc wheel removed the very points where thermal cracks usually started. The result was a wheel that demanded less attention in the shop and inspired new confidence out on the rails. For the first time, engineers had a reason to believe that a locomotive's wheels could last for years, not just months, before needing major repairs. Doubts echoed through every railroad boardroom as word of the disc wheel spread. Chief engineers pored over blueprints and shook their heads. The old rules warned of disaster, they said. A solid steel wheel would be too heavy, stressing axles and rails beyond safe limits. Worse, without spokes, there was nowhere for heat to escape. A single long, punishing run could warp or crack a disc wheel from the inside out. Letters and memos from mechanical departments spelled out the risks in careful detail, predicting catastrophic failures and expensive recalls. Yet, as the first disc wheels went into service, something unexpected happened. Maintenance shops began logging the numbers. Instead of the usual parade of cracked spokes and failed joints, the new wheels kept rolling. Where a spoked wheel might last 2 or 3 years before needing major repairs, the ledgers now showed disc wheels running for 6, 8, even 10 years with little more than routine inspections. The predicted thermal cracks failed to appear. Wheels that should have been warped by heat came back from long hauls nearly as true as the day they were cast. Mechanics grew quiet, then curious. Reports from the field started to pile up. Fewer breakdowns, less time spent swapping out damaged wheels, and a marked drop in the number of emergency repairs. Workshop ledgers, once filled with entries about spoke failures and rim cracks, now recorded months with no incidents at all. On some lines, the cost of wheel maintenance dropped by half. Engineers who had once laughed at the idea of a wheel with no spokes began to take notice. The numbers spoke louder than any argument. By the time the third or fourth set of spoked wheels had been replaced on older locomotives, the original disc wheels were still in service, their surfaces burnished but unbroken. The old objections, too heavy, too rigid, too risky, had been overruled not by theory, but by the steady hand of the maintenance ledger. The industry, driven by hard evidence, started to shift. What began as an experiment was fast becoming the new standard. By the mid-1930s, the disc wheel was more than a technical curiosity. It was everywhere. Major railroads moved quickly to retrofit their fleets, sending thousands of locomotives through the shops for new wheels. The Pennsylvania Railroad and Union Pacific led the charge, each embracing the solid disc as a symbol of modernization and reliability. Locomotive after locomotive from coast to coast traded its old web of spokes for the clean, unbroken face of steel. This was not a quiet revolution. The switch to disc wheels played out in full view of the public right as America's streamliner craze took hold. The Milwaukee Road's Hiawatha and New York Central's 20th Century Limited became icons of speed and style, their smooth disc wheels gleaming beneath sweeping Art Deco shrouds. Posters and magazine covers celebrated these trains as the future, sleek, fast, and impossibly modern. The wheels themselves, once hidden in shadow, became part of the visual language of progress. Railroads weren't just chasing fashion. Competing designs flooded the market, each with its own twist on the disc concept. Scullan's original solid disc was joined by the box-pock wheel from General Steel Castings. With its distinctive box-shaped cutouts and the Baldwin disc, favored by Union Pacific for some of its fastest locomotives. Each variant promised better balance, reduced vibration, and longer life, qualities that mattered as trains pushed for higher speeds and tighter schedules. The box poke, in particular, caught on with engineers who valued its lighter weight and ease of counterbalancing, earning a place on giants like the Union Pacific Big Boy. By the end of the decade, the spoked wheel was fading from the American landscape. Workshops that once specialized in patching up cracked spokes now focused on fitting disc wheels by the thousands. The shift was so complete that for a generation, the sight of a solid wheel meant not just strength, but style. The disc wheel had moved from the back rooms of the shop floor to the front lines of American culture, rolling beneath the most famous trains of the era. By the end of World War II, American railroads faced a new reality. Diesel-electric locomotives were no longer experimental. They were rolling out by the hundreds, backed by procurement memos and long-term contracts from every major line. The old steam giants, with their intricate webs of rods and massive driving wheels, suddenly looked outdated next to the clean lines and steady hum of diesel power. Management saw the numbers. Diesel units could run farther between overhauls, required less water and coal, and cut labor costs from the roundhouse to the main line. Between 1945 and 1955, the shift was relentless. The Pennsylvania Railroad, Union Pacific, and Southern Pacific all began retiring their steam fleets, ordering new diesels by the dozen. In 1949 alone, the Pennsylvania Railroad's annual report listed diesel purchases that would eventually sideline hundreds of steam locomotives. This new technology changed everything about locomotive design, including the wheels. Steam engines needed huge drivers, often 6 feet in diameter or more, to turn piston thrust into speed. Disc wheels, with their balance and durability, were perfect for this job. But diesels did not need them. Their traction motors powered smaller wheels, arranged in sets of 4 or 6, each turning independently. The stresses that had once cracked spokes or tested the strength of a disc were simply gone. Maintenance departments, once devoted to balancing and truing massive drivers, now focused on new problems, traction motors, electrical systems, and different kinds of bearings. The disc wheel's reign ended not because it failed, but because the world around it changed. The last great steam locomotives rolled into storage yards, their solid wheels still gleaming under layers of dust. Procurement records from the early 1950s show a steady decline in orders for disc drivers, replaced by contracts for diesel truck assemblies and replacement axles. The technology that had once defined modern railroading faded almost overnight, its purpose erased by a new era on the rails. Across North America, a handful of steam locomotives still thunder down the rails, their wheels cast in solid steel nearly a century ago. At places like the Railroad Museum of Pennsylvania, the Illinois Railway Museum, and Steamtown National Historic Site, visitors can stand inches from these survivors. Locomotives whose Scullan, Boxpock, or Baldwin disc wheels have outlasted entire generations of railroaders. Some of these wheels have been rolling since the 1920s or the 1930s. 80, even 100 years on, they show the scars and shine of hard service, but their basic strength remains untouched. Heritage railways run excursions using these original wheels, proof that the right design can outlive the technology that made it famous. The lessons behind their longevity aren't locked away in blueprints or hidden in museum displays. They're written in the steel itself, visible in every smooth rim and unbroken web. First, eliminate weak joints. By casting the wheel as a single piece, the disc design erased the failure points that doomed spoked wheels. Second, distribute stress evenly. Instead of forcing loads through narrow bridges of metal, the disc shares every shock and strain across its entire surface, preventing cracks from ever finding a foothold. Third, favor simplicity over complexity. The disc wheel's clean lines and solid construction made it easier to balance, easier to maintain, and less prone to the endless repairs that once filled railroad workshops. These principles didn't fade with the steam era. They carried forward, shaping the way engineers approached wheel design in trucks, heavy machinery, and even modern trains. The disc wheel's story isn't just about a vanished technology, it's about the power of questioning tradition and trusting what the evidence shows. The locomotives that still run on these wheels are more than museum pieces. They're living proof that when the right idea meets real-world testing, it can last for a lifetime, and sometimes far beyond. Innovation often vanishes when its purpose fades, but its lessons remain. Today, every wheel that carries weight, on rails or roads, owes something to the disc wheel's radical simplicity. When accepted truths are challenged, entire industries can pivot overnight. The real legacy isn't steel. It's the reminder that progress rarely looks the way we expect. What other impossible solutions are hiding in plain sight? Thanks for watching.